Thank you very much. Thank you, Alessandro. I thank you for having me here. It's a pleasure, and it's the. Now, this could destroy the whole thing. There you go. It's the first time I'm here in Bologna for scientific purposes, and I'm impressed by the size of the institute, by finding so many people that I crossed paths in the past, and now they're all here in Bologna. It seems to be a very nice aggregation point. So as Emanuele said, I am NYU AD, so this New York University Abu Dhabi. So usually it's good to put things in perspective. I'll let you know where I am physically. So this is, well, this is Italy, right? This is Abu Dhabi. Abu Dhabi is here, is the capital city of the United Arab Emirates. If I zoom in, that's the Arabic Peninsula. And since 2008, New York University has opened a campus in Abu Dhabi. And if you want to know why, I would be happy to tell you, because it's an interesting story. So this is a picture of Abu Dhabi. It's a very nice city. You're all invited to visit. We have a very nice corniche, which is this road that runs along the sea, classical skyscrapers from modern cities. That's the campus at NYU Abu Dhabi. It's quite large. We have 2,500 students across all disciplines, from science, arts, humanities, and engineering. We also have a very lively theater. It's a very nice place to visit. And if you're interested, please let me know. We have a large series of colloquia. That's just show you where our students are coming from, and it's literally all over the world. So local students from the Arab Emirates are a minority. We have about 10% of students from the UAE, and the rest is literally from all over the world. And this, of course, creates a lot of challenges, especially when you teach, because you get students from all possible backgrounds, and that's both ways, both challenging and interesting. Within the NYU Abu Dhabi University, we also have a Center for Astroparticle and Planetary Physics, a bit of a long name. Now it's going to be changed as January 1st, most likely a Center for Astrophysics, to make it shorter and more compact. And I'm the director of the center. And again, the center offers a lot of possibilities for sabbatical, for short or long visits. So just reach out to me if you're interested in spending some time in Abu Dhabi, especially in winter. Abu Dhabi is an extremely pleasant place to visit. Last thing is that on January, we're organizing a large international conference. Here's the poster, and it's about timescales in astrophysics. So it's quite broad, and we cover practically, instead of focusing on objects, we just focus on timescales. So we go from milliseconds up to the Hubble time. So if you want to attend, present, the deadline for submitting abstract was this Monday, but if you want to submit an abstract, just go to the website where the system will still accept you. And we'll be happy to consider that. And we have a lot of people from all possible backgrounds. For example, Risa Resconi, dark matter research, Rosalba Perna, high energy astrophysics. And you see here the speaker from Mark Kramholz, Girish Kulkarni. So we cover practically the whole spectrum of phenomena happening in astrophysics. So please reach out to me if you are interested. Now, so this is a picture from the Hubble Space Telescope. And I think we all agree that we have a quite good understanding of what are the elements in our world, right? We know that atoms, things we are familiar with, only 5%, and the rest is dark matter and dark energy. And we live in the precision cosmology era. And I heard this many talks and seminars where we know the main numbers that characterize our universe with extremely high precision, right? And then for young people, this might be normal, but there are people in this room that are as ancient as me, and they remember that in the good old times when you were running simulations, right? Not only you were running simulation with different parameters for the simulation, but you also had to cover many different cosmological models. This is just a table from a paper from Matthias Bartmann, 1998, and you see that not only it didn't put any errors on those numbers, right? But look, for example, the total amount of matter. He had 1, 0.3, 0.7, 0.30. So it was still considering open cold dark matter. So in the next 20 years, we went from guessing those numbers within like factor of 1 to extremely high precision. But sometimes I wonder if this is truly high precision cosmology, or actually what we have is just a precise measurement of our ignorance. Because it's true that those numbers have boiled down from being around 0.7 to this very high precision. But if you think about that, our knowledge about what is dark matter is the same as 1998. We haven't gained that much. The only thing we've been able to do is to remove some models, right? Some models are not viable anymore. But if you ask physicists what is dark matter, the answer you get now is the same they would have given you in 1998. We haven't gained much. Okay, so what do we think is dark matter? The leading model is called cold dark matter, and it's based on 3 properties. The first one, that dark matter is cold. So at the coupling, all the velocities were given by the gravitational collapse. It's dark, doesn't interact with ordinary matter, and is collisionless. So it doesn't, the cross-section with ordinary matter is conditional. And with these 3 models, with these 3 simple assumptions, we can create a very nice paradigm about structure formation. We know that structure formation proceeds bottom up. So we have small objects merging and forming larger ones. And we are able to reproduce the large scale structure of the universe. Now, if you go to talks about models which are alternative to cold dark matter, they will always start telling you that this picture is nice, it works fine, but there are usually a lot of problems, cold dark matter. So if you look at this kind of papers or seminars, they always tell you dark matter works very well on large scales, but faces many challenges on small scales. That's usually the first line in any paper that is beyond cold dark matter. And those problems, they have been named in all possible ways, like missing satellite problem that goes back in 1999, diversity rotation curves that's been brought forward more recently, too big to fail, and core cusp dilemma, galaxies without dark matter. And all those ideas are always there to tell you that there is a need to go beyond cold dark matter. So what I want to address in my talk is that, is this need really there? Do we really need to go beyond cold dark matter? Is there an evidence, an experiment that tells us that no, cold dark matter cannot be the right one? Now, the problem is that if you have all these problems, every time you're trying to find a solution or to address one specific of those, right? But I want to try to convince you that those problems, they just stem out always from the same fact. Okay, what is this fact? The fact is that dark matter halos are self-similar. Okay, or if you prefer, there is no specific scaling gravity. What does it mean dark matter halos are self-similar? I mean, we have here a lot of experts on dark matter simulation, right? Carlo, Marco, many others, Luca. And now I can ask you this. You see this. This is a dark matter density map of a dark matter halo. You cannot tell me what you're looking at. You can't. This object here could be what? Could be a galaxy cluster, 10 to the 14, making giant arcs, lensing, very important for cosmology. Could be a group. Could be hosting 15 to 20 galaxies like our local group, we will describe that. Could be the dark matter halo of the Milky Way. Could be a dwarf galaxy. You can't tell. And you can't tell me because dark matter is self-similar. So this object here, if you just change its mass by 6 or 7 orders of magnitude, it doesn't change. Okay. Yeah, there are some things that broke self-similarity, but if you just look at the picture, you can't tell. You can't. This self-similarity also reflects itself in many properties of dark matter halos. One is that they all tend to have the same distribution of mass. So if you look at the mass, this is the density starting from the center as a function of radius. All dark matter halos, they always have the dark matter, they have the same shape. This shape here, for example, it's sometimes useful instead of writing as radius and density to recast it in a circular velocity because it's something that you can access easily in observations. So this is a set of dark matter halos. They span 3 orders of magnitude in mass. And what we did was just to recast them as circular velocity, gm over r. The fact they are so similar means that I can collapse all of them in practically one line with some scatter that has to do with the concentration and the formation time of the halo. But you see that this scatter is factor of unity. And practically all those halos can be collapsed in a single, all those lines can be collapsed in a single line if I just rescale them, for example, the radius to the total radius of the halo and the circular velocity to the circular velocity at this specific radius. And why is this a problem? But this is a problem. Oh, sorry. The same things also applies to substructures. Right? If you look at this thing, you cannot count the number of subhalos and tell me if you're looking at the cluster or a galaxy, because regardless of the mass, for cold dark matter halos, they always have roughly 300 satellites between 10 to the minus 2 and 10 to the minus 4 of their own mass. So if the mass is 10 to the 14, you have 300, 10 to the 12, 10 to the 10. If the mass is 10 to the 10, you have 300, 10 to the 8, 10 to the 6. Okay. So why is this a problem? Well, the problem is very easy. that galaxies are not self-similar. And that's where everything breaks down. Galaxies are not self-similar. This is an example of rotation curve of galaxies. This is from a very nice paper from Oman 2015. So the points with the arrow bars are rotation curves of real objects. And what you see here is the best fit that comes from their simulations that's the ego simulation. And the problem is that the rotation curves of galaxies are very diverse. So some of them are gently rising, some of them are steeply rising. And it's impossible to fit all of them with a model called dark matter, which has no flexibility, because cold dark matter are self-similar. You always get the same. Okay, and that's where the problem arises. The same for substructures. I told you that the number of satellites is roughly 300, but the problem is that now if you look at observations, around the Milky Way, there are 50 galaxies, but around a big cluster like Abell 1689, there are 700 galaxies. So when you move to visible matter, the self-similarity is broken. You don't have the same number of satellites, say a few hundred, around the cluster or a Milky Way halo, okay, which is against what cold dark matter would do. So that's where the problems are. So if you want to go beyond cold dark matter, what you have to do is to break the self-similarity. That's the only way to save the day. And now, how do you break the self-similarity? Well, people usually try to break the self-similarity directly in the dark set. So what you have to do is to bring a scale into the problem. You have a problem which is scale-free, you have to bring a number, something that sets a scale. For example, if you have self-interacting dark matter, this number is given by the cross-section, right? You bring a new number into your problem. If you have fuzzy dark matter made on an axiom, something that I'm working with people here, for example, you have the de Broglie length of your particles. It's a number which is in the system. If you have other interaction in dark sector, again, you bring in new numbers that describe those interactions. And as I say, always you name it dark matter, right? There are more models outside for models beyond cold dark matter than people working on them. Okay, so you have a plethora. But there is an elephant in the room. So what if you can break this self-similarity not by changing the dark sector, but taking into account that you have galaxy formation? If galaxy formation can break the self-similarity, then you're done, right? You don't need to go into the dark sector. So how do you address that? Well, I have to introduce the simulation project that we have done at NYU Abu Dhabi. It's called NIHAO. NIHAO is an acronym that stands for Numerical Investigation of 100 Astrophysical Objects, but it also means hello in Chinese. And it's a collaboration between NYU Abu Dhabi and the Max Planck. So that's where I am now, where I was before. And this is the Purple Mountain Observatory in China with Professor Kang. That's a partial list of the people working on that. So what do we do in NIHAO? So the idea was to simulate a large number of high resolution galaxies. So you need a large number because if I told you that the problem is that galaxies are not self-similar, you need a large statistical number to capture the non-self-similarity. If you just run one Milky Way, what can you say about that, right? The Milky Way and Andromeda are very different galaxies, despite having very similar masses. So what we have at the moment, so the idea was to have the H stands for 100. Now we crossed 200 galaxies. This number is a bit out of date. This is one of our simulations. You see here just a stellar disk to show you that we get very nice thin disk galaxies. We go from Milky Way satellites to massive elliptical, so we have a very broad range of masses. That's everything we include in our simulations. If you're happy, I can give you more details. Otherwise, I think it would bore people that are not in the simulation business. So the whole point is that what we do is that at the same time, we follow the evolution of the dark matter, the gas, and the stars. Okay. So what you see here is the left is the formation of a galaxy, which at the end turns out to be a nice disk galaxy. What you see here is dark matter density, the gas temperature, and the stellar density. So we have all the three at the same time. And the idea is that can this part break the self-similarity in the dark matter? Okay. So it takes another half-life of the universe. I think we can skip it. That's again just for illustration purpose. This is a set of galaxies. The left one are real galaxies from mainly from the Hubble Space Telescope, and on the right hand, it's their counterparts in NIHAO. So one advantage that we have more than 200 galaxies is that we can find analogues of most of the galaxies that we see in the sky. For example, this one is very nice. You see, this is the interacting galaxies. You see here the companion, and we have something very similar in NIHAO. We have grand design spirals, the Sombrero galaxy, and so far so on. Okay. So there's one caveat that I need to bring up because it will become important later, that for people that are not familiar, when we ran dark matter simulations, we do things from first principles. We write the gravity equations and we let it evolve. when you run galaxy formation simulations, you have to take shortcuts. Why? So for example, that's how we do star formation and feedback in our simulations. So we have a gas particle, which usually is a typical mass, depending on the simulation. And we say, well, when this gas particle is cold enough and dense enough, it's going to make a star. So when the star is made, part of this mass stays gas, part of this mass goes into a star. And then the star is not a stellar, it's not a single star, right? It's a star cluster, so it has some mass. So we have an IMF. We can decide how many supernovae we have. The supernovae are going to explode, and they're going to put energy back into the system. So this energy goes back here into my gas particle, which is at some temperature and density, and just will move to another temperature. So that tells you how simple is the scheme that we use, and actually everybody uses in the business of numerical simulation. You can make it more complicated. You can add slightly more layers of subgrid physics, but that boils down to this, right? You have a gas particle, you have to decide when a star is made. And now this is a star forming region, right? That's a very famous picture from the Hubble Space Telescope. And now what you see here, this is the gas cloud, which has formed these young stars, which are now shredding apart the gas cloud. And what I want to make very clear that this amazing physics, it's encompassed in one single particle, right? So clearly there are things we can't simulate for first principle. We have to make decisions. So the first thing you have to do after you run a simulation is to validate it, right? You have to make sure the simulations you get, it's good against observations. And what we use is a series of scaling relations observed from real galaxies. For example, this is the relation between the total mass of a galaxy, the stellar mass of a galaxy by abundance matching. So that's where real galaxies live. This line here, it's based on a combination of results from lensing, satellite dynamics, and name it. But real galaxies that live around this line, and you see the NIHAO galaxy, that's original NIHAO 1 paper, there were 82 objects, they all live around the line. And then we have tested our simulations against classic relations, for example, Stanley-Fisher relation, that's the gas disk versus cold gas mass relation. And again, for example, here you can see that black is the, red is the observations, and black is the results from NIHAO, depending on different resolution. And you can see we can get the slope, the 0 point, and even the scatter observation. So NIHAO galaxies are reasonable galaxies. So that's a list of the papers. I used to show it, but then the list is becoming too long because now we recently reached NIHAO 28. So I don't want to bother you with going to 28 papers. The papers, they have very different approach. Some of them are about galaxy formation, some others are more about, for example, the gas, some others are more about local properties or dark matter, and so far so on. So if you're interested, there's a long plethora of papers, and they all start with NIHAO and a number, so they're very easy to find on the archive. So we have real now and simulated galaxies, and we can ask ourselves, how did it go with the whole business of self-similarity? So this is the plot I showed you before. This is for galaxies which is IC 2574, which is notoriously different to be captured by model space and cold dark matter. And that's the results we got in NIHAO. So that's a rotation curve. Those points here are the same as those points there, just different observations, but it's the same galaxies. This is the line that we got if we run a dark matter only simulation. And that's a spectrum. So similarity, the line is always the same. We can go through the data. But this is the distribution that we get once we run the galaxy formation. So we are able to reproduce these galaxies. So what's happening here, we are able to change the distribution of dark matter from the black to the blue line. And now, what I can show you in this plot, this is exactly the idea of breaking the self-similarity. So what you have here is the ratio between the velocity dispersion, the rotation velocity in the run with galaxy formation, hydro, and without. If self-similarity was not broken, all those lines will again collapse into one. What you see here as a function of radius is that in the inner part, which is exactly where galaxy formation happens, those lines, they open up like a funnel. That means that not only we are breaking the self-similarity, but we are breaking the self-similarity in different directions for different objects. So some objects, they have more velocity in the center, meaning more mass. Some objects have less velocity in the center, which means less mass. And you see there's a gradient of color, and this has to do with the efficiency of star formation. So how good is a galaxy to make stars? So yes, we can break the self-similarity. Now, how do we do that? How is galaxy formation able to change the distribution of dark matter? And I'm gonna illustrate that with a movie. So the idea here, what you see here is the gas distribution in a dwarf galaxy. What you see here is the effect of supernova explosion. So the gas is going in due to gravity. When it goes in, it gets very dense. And when it's very dense, star formation happens, supernova explodes, and then the gas is pushed out. So what the gas is doing is going in and out, in and out, in and out from the dark matter halo. What does the dark matter see? What the dark matter sees is a time-changing potential, right? The potential is changing, but it's changing on two very different time scales. When the gas goes in on the dynamical time of the halo, right? So it's a long time scale. The gas needs time to go in. When the gas goes out, it goes out very quickly because it's an explosion. So what you happen is that the effect of gas going in, it's adiabatic, where the gas of going out is a non-adiabatic process. So when you have a non-adiabatic process, you know it's an irreversible process. So the dark matter is truly, the dark matter sees the potential going up and down, up and down. But when the potential goes up, so it's deeper because there is more gas, it does very gently. When the potential goes down, it does very quickly. As a net effect, the expulsion of gas is able to push out the dark matter because dark matter reacts by moving out when the potential is shallow. And the other thing that is important here is that you now can imagine that every galaxy has its own star formation history, has its own path of formation, has its own number of supernovae. That's why you break the self-similarity. It's true that all galaxies have the same dark matter distribution, but as we know, as astronomers, each galaxy has its own path to star formation. And that's why self-similarity is broken, because each galaxy becomes unique in this case. And that's why we get galaxies like IC, I already forgot the number, 2574, and we got other galaxies, because each galaxy is different. And with NIHAO, since we have 200, we can find counterparts of most of them, okay? So what happens, for example, if you want to try to quantify that, I told you that all galaxies, they have this, dark matter have the same density profile. The slope is usually characterized by alpha, which is the logarithmic slope. For the famous Navarro-Franken-White profile, the slope should be -1. So if you look at dark matter only simulation, you would expect all halos, regardless of their mass, to have slope of -1. Now, if you look in NIHAO, you find this very funny shape. Okay, so that would be the prediction of a cold dark matter universe. Everything around -1 is asymptotic, so actually it's -1.5 because this measures the sum fraction of the via radius. But what we have in our on our simulations is that this alpha is keep changing, and it changes in a very specific way, which has to do with the fact that some galaxies, they reach the best ratio between how much dark matter there is and how many supernova explosions there are. And then as you can imagine that if you have very little dark matter, if you have a lot of dark matter, very little stars, right? That's the dark matter halo. That means here that typically you have per mil or fraction of per mil of mass in stars. You have too few supernovae. Then you grow in mass and you have the right combination between number of supernovae and the total dark matter mass. Then you become very massive, like the Milky Way. And so now the supernovae are changing the potential, but now the potential is done by dark matter and stars. And here, for example, you have a bit of regrowth because you have AGFP. Okay, I don't want to go too much in details. What I want you to convince is that self-similarity is broken, and it's broken in a very specific way. The same happens for the satellites, and again, this is because might be a bit bright here. Anyway, so you have here the formation of a dark matter halo, and then you have here the formation of the stars. And now you see that star formation is not happening in every dark matter satellite, right? There are satellites like this one, this little one up here, that do not have a counterpart in the stars. And this has to do to a plethora of phenomena. The fact that there is randomization of the universe, that little satellites have to fight against the gas temperature, which is quite high for them to make stars. There are supernova explosions that kick out a lot of gas from the satellites. The point is that galaxy formation naturally, it's breaking the self-similarity. And that's why we don't have the same number of satellites around the galaxy and a galaxy cluster. Because you can imagine that if this object now would be a galaxy cluster, this thing would be 10 to the 14. This object here would be 10 to the 12. And so each of these little guys will be around 10 to 11. And we know that if you have dark matter halo 10 to 11, it's bound to form substars. Okay. So star formation, again, doesn't happen in all halos at the same time. Star formation is not democratic. It prefers to go some halos than others. That's why at the end, you have like 10, 15 satellites in stars around an object that has planets. For example, here you see all this population of dark satellites who do not show up in the star formation. This is just a quantification as a function of dark matter halo. We can tell what's the probability for a given dark matter halo to be dark or bright. So that's a fraction of dark satellites. So if you are above 10 to the 10, each dark matter halo has stars. If you are below few 10 to the 7, no dark matter halos as stars, and in between you have a given probability. So self-similarity is broken, which brings me back to the initial plot. What were you looking at? Anybody there cares to guess? What was this object? That's the material I showed at the beginning. I think that if I've shown this maybe to Massimo or others, they would go for galaxy clusters. It's just a bias, right? They work with galaxy clusters, they would say galaxy cluster. This object here, it's a dark matter of 10 to the 9. It's the host of one of the smallest galaxies we have in NIHAO. So that's the visible counterpart of this object. This object has zero gas, all the gas is being kicked out by supernovae, and it has a bunch of stars in the center. So you see here that only this big halo here has been able to make stars, not even its companion. This companion here, it looks close, but actually it's a bit far away in 3D. And just to give you an idea, here the ratio between stellar and dark matter halos is 10 to the minus 5. And it's a dwarf spheroid. It's a dwarf spheroid, yes, one of the smallest we've been able to form. And we wrote a few papers about this kind of dwarf galaxy. So this object here, it's a dwarf galaxy, and it was impossible to guess from the beginning. Well, is everything solving galaxy formation? Do we know all the answers? But the answer is no. There are still things we can't replicate in galaxy formation. This is a plot from a paper which is today on the archive from my postdoc, Nick Arora. And what we did was to compare NIHAO, those are the magenta points, with manga. So what you see here, there's a cloud here is the results from manga. There are like 30,000 galaxies in this cloud with some selections. And this is just scaling relations. These are a set of relations. For example, this is the, what is Tully-Fisher? This is the stellar Tully-Fisher relation, so P versus mass of stars that I showed you before. NIHAO does very well. We have, what is that here? We have central density versus stellar mass. NIHAO does very well. And you see some panels are blacked out because those are blacked out because they are where NIHAO does less. So there are in our simulations, they don't reproduce everything perfectly, right? For example, star formation rate, stellar mass, which seems to lack galaxies in the top here. This one also is a bit offset. The point is that now what we have are small discrepancies. And what I want to argue is that those discrepancies, they don't require you to change cold dark matter. Most of those discrepancies, they come simply from the fact that we are condensing a lot of physics in one big file. So I don't want to give you the example that the idea that everything is set. We are very far away from that. But all the problems are mainly due with our inability to do galaxy formation for first principles. So better computers, better ideas, better codes will bring us there. So in the last 15 minutes, I just want to talk about the fact that despite that, every now and then there are new papers in the archive that challenge cold dark matter and they say cold dark matter is dead. And this is a cyclic thing, right? If you've been in the business long enough as I've been, you will see that yearly there's a paper that says, okay, it's done. Here's the counterproof. There is no cold dark matter. Okay, so there's a sort of need to prove cold dark matter wrong, especially if you want to publish in high impact journals like Nature and Science, that most of the time they have wrong results there, but that doesn't matter, right? When you apply for tenure or promotion, if you have Nature papers, it's usually good. So I want to just spend the last 15 minutes on the case of galaxies without dark matter. I don't know if you've heard about this set of papers, but they made quite a splash a few years ago. So this is a lecture to Nature. It's a galaxy lacking dark matter. Peter Van Dokkum is the first author, his collaborators. And then after this first discovery, this first galaxy, he found the second galaxy with very similar properties that he published on it. So what are those galaxies without dark matter? I mean, in the general picture, you should not have a galaxy without dark matter, right? Dark matter forms first, makes the potential well, gas comes in, makes stars. So every galaxy must have dark matter. Okay. What Peter found was this specific galaxy, which he called DF2, that has no dark matter. How does he know? Well, he's lucky enough. There are about 12 globular clusters around this galaxy. And so he's using the velocity dispersion of the globular clusters. So the velocity along the dispersion on the velocity along the line of sight of the globular cluster, not the intrinsic one of the globular cluster, to see how much dark matter there is in this galaxy. So that's very simple. The dynamical mass virial theorem is sigma square RG. So he has sigma from 15 points. He has the radius, knowing the distance. I will not argue about that. He knows the gravitational constant. And he gets the dynamical mass of this object within 7 kiloparsec. That's the farthest globular cluster. It's 2 10⁸ solar masses. Why is this a problem? Because he also has the light, and he finds that the total stellar mass in this object, it's roughly the same order of magnitude. Okay, so technically dynamic tells me there is very little dark matter within 7 kiloparsec. So the first question is that, can you get a galaxy like this in a universe dominated by dark matter? Well, we tried. As soon as the paper came out, I made this paper. In this paper, you have the velocity dispersion based on 15 tracers, as it did, as a function of the stellar mass of the object. And he found values about between 5 and 10. He has 2 galaxies, but for every galaxy, he has 2 measurements. So I consider them as 4 independent points, just for sake of simplicity. You see, they're aligned at the same stellar mass. And these are the results from NIHAO. So in NIHAO, when we reach stellar masses of 8, 8.5, we have velocity dispersion typically of 25 kilometers per second, very lower than what we found. That's because we have typically at 7, 8 kiloparsec, dark matter beats baryon 50 to 1. Okay, there's 50, 25 more times dark matter than there is. Where he found they are the order 1, the ratio. So is this a problem?
This proves not only that dark matter, but also small.
It does, true, yeah. What is, and it will still disprove small. I mean, I will show you it does not disprove dark matter, but with MOND it's still there, yeah, but what happens here is that, I mean, face value, this is a problem, right? There's no way I can do that in NIHAO. So, but let's see how you should always, you see, when you see those big claims, you should start to dig it a little bit more and ask yourself, was that the whole story? Well, it turns out that this little galaxy, which is the F2, the one you observe, it's not isolated. It's actually a satellite, or it's very close to a much more massive galaxy, which is a massive elliptical, which has a mass about 10 to the 4 times larger than this galaxy here. So could it be that you have some tidal stripping? And of course, this is discussed in the paper, but the argument from Van Dokkum is that, look, the typical size of my globular cluster is 14 kiloparsec. And if you compute what's the tidal radius for this object, given the vicinity, it's order of twice this distance. So if people are not familiar with the idea of tidal radius, in a perfect spherical cow world, it tells you that everything which is outside this red circle, which is tidal radius, can be removed, can be influenced by the vicinity of the other object. Everything which is inside, it's unperturbed. So his argument says that, look, the tidal radius is so much bigger than the radius I use for my galaxy, I should not care about tidal effects. Is this true? Well, I didn't believe that for good reasons. And so what we did, we took the 4 of our galaxies from NIHAO, 3 actually, and we threw them a potential which mimics this bigger object, which is around, which is the bigger massive galaxy, the NGC 1052. And we shoot them with orbits such that we go very close to the central object. Okay, this is an example of 3 of those orbits. So you see the galaxy comes in, the central object is in 0, 0, gets deflected, oh well, then comes back a little bit. So what do we found? Well, we found that as soon as we start doing that, we saw that the velocity dispersion of the stars drops dramatically. So here there is a peak, which is the first passage. The velocity starts at 25. And then remember, that's the value we start, 25. And then after passing through, it drops down and it goes to value around 5, 8, which are perfectly consistent with the observation of Van Dokkum.
Because of mass loss.
If there is mass loss within the tidal radius, which in principle, as I say, in a spherical cow world, that should not happen, right? Everything which is the tidal radius, within the tidal radius should be protected. And most interesting, we only see tidal loss in the dark matter, not in the stars. So somehow gravity is selecting only dark matter and not touching the stars. How is that possible? Yeah, it of course depends on the orbit, depends on the galaxies. Not every orbit, not every galaxies go through the point. So the idea is that you have to bring this 25 down to 8. And once this happens, you can see immediately that the ratio between dark matter and stellar mass, which I told you starts between 25 and 30, it drops down to number of order unit. So how does that happen? Well, the reason is that the world is not spherical cow. That's why you need cosmological simulations when you do this kind of things. So that's the tidal radius, and it is that if you are a dark matter particle and we are within the tidal radius, you are protected. You cannot be removed. But dark matter particles, which is moving this way, they are not on circular orbits, on contrary of stars. So dark matter particles, they have very complicated orbits, usually like bretzel shape, right? This typical German cake. Which means the dark matter particle, which is today within the tidal radius, can be outside the tidal radius later on in its life. And so what is happening that this particle here, it's inside, so you think is unperturbed in your spherical cow model, but then it goes outside, and when it's outside, it's removed. What does it mean? That this particle was then supposed to come back here, but it will be missing. And so the net effect is that the mass within the tidal radius, it's reduced. This clearly does not happen to the stars because the stars are not on crazy orbits, right? The stars are formed in the center of the galaxy. They always stay within the center of the galaxy. So as time goes by, stars are always inside. When dark matter particles they go outside, they get removed, they never come back. And the net effect is that the total dark matter mass within 7 kiloparsecs decreases. So low MBO, we can take galaxies that have much more dark matter than what Van Dokkum has seen and bring them exactly in agreement with the points from Van Dokkum. Okay, so we can create a galaxy without dark matter in a dark matter dominated universe. And so what does it mean? It means that all those claims that people make usually are based, that's been my experience so far, on very simple assumptions that work in a spherical cow world, they don't work in the real world. And that's the problem we call dark matter. It's such a famous model that people spend a lot of time trying to kill it with evidence that when you look carefully, it's very weak. Now, something we did not address in our paper is that how likely is this orbit to happen? In physics, you just show something happens once, and you can assume it happens many times. But of course, there is a frequency, right? Is this super unlikely to happen? And there's been a follow-up paper by Jorge Moreno, which is a great paper, used cosmological simulation, and he showed that per galaxy, like the one that Van Dokkum showed, so you should expect 2 to 5 galaxies with very little dark matter, and he showed. Okay, even statistically, that works. That was not addressed in our paper. That's a work by Moreno collaborators. Yeah, I'm done. So I can go down now to my conclusion. We can have an extended Q&A. So what is the conclusion? My conclusion is that I don't see any clear evidence from observations, so any fact that tells me we need to change cold dark matter. Okay, and I think that all the possible remaining discrepancies that are there are just because we cannot do galaxy formation for first place. So remember, if you want to change cold dark matter, you are changing the backbone of our understanding of cosmology. As soon as you touch cold dark matter, you start touching like things like the CMB, right? Large scale structure of the universe, 2-point correlation function. Things that are very good. They're very in good agreement with data. So before doing that, you want to ask yourself, is there anything else that might change or explain my observation? Think about the galaxy without dark matter. You need to throw dark matter down in the garbage, right? What you have to do is just think carefully, is this galaxy isolated? Could be tidal effects and so on and so on. Okay, that seems to be very great, but this includes galaxies without dark matter. Is then cold dark matter is the answer? But that's where things become very problematic, because the answer is no, not at all, from galaxy formation point of view. Why? Because the fact that we cannot disprove cold dark matter doesn't mean cold dark matter is the right answer. Science doesn't work like this, right? You need one data point to disprove a theory, but to confirm a theory, there is no sufficient number of data points. But you're still gathering them, and you see where it works. And what is a bit sad is that when people talk about cold dark matter, they think usually, especially particle physics, to WIMP-like objects. Those are mass of those objects is around GeV, maybe even 100, maybe even larger 100 GeVs. And this is what everybody's looking for in underground experiments. Grand Sasso laboratories, Dune, the Dam. I mean, all those people, they're all looking at this kind of particles. So GeV scale. But from a point of view of galaxy formation, anything with the mass larger than 5 keV for a thermal candidate would work equally good. So when I say cold dark matter, I'm not saying that the dark matter is a WIMP. The dark matter has a given scale. I'm telling you from 5 keV, 10 keV, up to GeV, TeV. So we're talking about 6, 8 orders of magnitude. It's exactly the same for galaxy formation, which is quite sad if you think about that. That means we have no handle to tell a particle physicist what dark matter is. And this is another talk that I give, which is quite depressing, so I decided not to give it, that I think we will not learn anything on cold dark matter for the next 20 years, astro-wise. Okay, so cold dark matter is not wrong, but it doesn't imply that it's the correct model, and I'm happy to stop. Thank you very much.
It's very nice tool. So we are